Hello and welcome to G Fun Facts Online. Today we are leaving the familiar territory of rock, ice, and gas behind. For decades, our understanding of the universe was shaped by what we saw in our own backyard. We looked at Earth, Mars, and Venus, and we saw silicate rocks. We looked at Jupiter and Saturn, and we saw massive balls of hydrogen and helium. We searched for water, the universal solvent, and oxygen, the breath of life. We assumed that planets, wherever they formed, followed the same recipe book as our solar system. But in the deep dark between the stars, nature has been cooking up something far more alien. Something that challenges the very chemistry of planetary formation. We have entered the era of the carbon worlds. In the dying days of 2025, the astronomical community was shaken by the discovery of a world known as PSR J2322-2650b. It is a world that defies nearly every rule in the planet hunting handbook. It is shaped like a lemon. It orbits a dead star, and its skies are filled not with water vapor, but with soot and diamonds. This is the story of those diamond skies. It is a journey into the crushing pressures of alien atmospheres, the delicate dance of light and chemistry, and the revolutionary eyes of the James Webb Space Telescope that have finally peeled back the haze. Let's start with that lemon-shaped oddity at the edge of physics. The discovery of PSR J2322-2650b began with a flicker in the data. Astronomers were training the golden mirrors of the James Webb Space Telescope on a pulsar located 700 light-years away. Pulsars are the crushed cores of dead suns, rapidly spinning neutron stars that blast beams of radiation across the cosmos like a lighthouse. They are the most precise clocks in the universe. When a pulsar spins, it ticks. If that ticking skips a beat, it means something is tugging on it. In this system, the tug was violent. Orbiting this city-sized stellar corpse was a planet the mass of Jupiter, but it was whipping around its host at a suicidal proximity. The gravitational tidal forces in this system are so immense that the planet is literally being pulled apart. It is being stretched into an oblong, rugby ball shape. The press affectionately dubbed it a lemon, but the violence of its shape was only the beginning. When the telescope's near-infrared spectrograph tasted the light filtering through the planet's edge, it didn't find the usual water vapor or silicate clouds we see in our solar system. It found carbon. Rivers of it. The atmosphere of this world is a chemical nightmare dominated by helium and pure molecular carbon. This is a composition that technically should exist in standard planetary formation models. In the crushing depths of its atmosphere, where pressures mount to millions of times that of Earth, this carbon doesn't just sit there. Models suggest it condenses. It crystallizes. On the day side of this planet, temperatures soar to over 3,700 degrees Fahrenheit, vaporizing everything. But as winds screech toward the permanent night side at supersonic speeds, the carbon cools. It forms clouds of soot, blacker than the darkest coal. And as that soot falls, compressed by the gravity of a Jupiter-mass world, it undergoes a phase change. The soot hardens. It becomes clear. It becomes a diamond hail, falling into a magma ocean of liquid carbon. This is not a rare anomaly. It is a window into a new kind of planetary science. To understand why a planet would rain diamonds, we have to look at the kitchen where planets are cooked. This is the story of the carbon-to-oxygen ratio, arguably the universe's most important fraction. When a star forms, it leaves behind a swirling disk of gas and dust called a protoplanetary disk. For years, we assumed that most of these disks looked like ours, which was rich in oxygen. In our solar system, oxygen is the bully. It grabs every loose carbon atom it can find to form carbon monoxide or carbon dioxide. Whatever oxygen is left over bonds with hydrogen to make water, or silicon to make rocks. Because oxygen outnumbers carbon here, our planets are made of sand, granite, and water ice. There is very little free carbon left to do anything interesting. But the galaxy is diverse. Some stars form in clouds that are richer in carbon. If a protoplanetary disk has a carbon-to-oxygen ratio greater than 0.8, the chemistry flips entirely. In these systems, carbon becomes the bully. It grabs all the oxygen to make carbon monoxide. But now, there is leftover carbon. This free carbon has no oxygen to bond with. So instead of forming silicate rocks like sand or quartz, it bonds with itself or with metals. Instead of sand, you get silicon carbide, also known as carborundum. Instead of granite mountains, you get mountains made of solid graphite. Instead of water oceans, you might get tar or liquid hydrocarbons. And deep underground, where pressure is high, you get diamond. Two pioneers of exoplanet science, Mark Kuchner and Sarah Seeger, coined the term carbon planet back in 2005. For years, it was just a hypothesis. Now it is an observed reality. Before we found the lemon planet, there was 55 Cancri e. Located 41 light-years away, this super-Earth is about twice the width of our planet and 8 times its mass. It orbits its star so closely that a year lasts just 18 hours. It is tidally locked, meaning one side faces the star in an eternal, scorching day, while the other is frozen in endless night. For a long time, we thought 55 Cancri E might be a water world. But in 2011, detailed measurements of its radius and mass suggested it was too dense to be water, but too light to be pure iron. The math pointed to a composition that was largely carbon. Imagine standing on the night side of 55 Cancri E. You would need a very sturdy spacesuit. The ground beneath your feet wouldn't be dirt. It would likely be a crude form of graphite, essentially pencil lead. As you walk toward the Terminator line, the border between day and night, the ground changes. The intense heat from the day side and the internal pressure from the planet's mass act like a forge. The graphite crust likely thickens and compresses. Kilometers beneath the surface, geologists believe there is a mantle, not of molten silicate rock, but of diamond. In 2024, observations detected a secondary atmosphere around this world, likely outgassed from a bubbling magma ocean, but this isn't silicate lava. It is a slurry of carbides and carbon. The atmosphere is rich in carbon monoxide and hydrogen cyanide, a deadly, toxic blanket. Recent data from the James Webb Space Telescope suggests the planet might be losing and regrowing this atmosphere in a cycle of destruction and rebirth driven by the star's flares. But the core truth remains that 55 Cancri E is a gemstone world, a celestial jewel worth more than the GDP of the entire Earth, yet utterly uninhabitable. If 55 Cancri E is a diamond, then WASP-12b is the velvet box. WASP-12b is a hot Jupiter, a gas giant orbiting perilously close to its star. It is so hot, around 4,000 degrees Fahrenheit, that it glows faintly red. But its most striking feature is its albedo. WASP-12b is pitch black. It reflects almost no light. Why? Because its atmosphere is a carbon trap. Discovered to be the first carbon-rich world, WASP-12b has a carbon-to-oxygen ratio greater than 1. Its atmosphere is dry, remarkably depleted of water vapor. Instead, it is filled with methane and acetylene. Methane is a powerful greenhouse gas, but acetylene is the key to the darkness. In high-temperature atmospheres, acetylene acts as a precursor to soot. Just as a candle flame produces black soot when there isn't enough oxygen to burn the wax completely, WASP-12b's atmosphere is constantly burning in a low-oxygen environment, generating a haze of carbon nanoparticles. This soot absorbs starlight efficiently, heating the planet even further and causing it to swell up like a pufferfish. It is a world of smoke and shadow, where the clouds are made of charcoal. Now, let's talk about the physics of diamond rain. The idea didn't actually start with exoplanets. It started in our own backyard. Uranus and Neptune, the ice giants of our solar system, are blue not because of water, but because of methane in their atmospheres. Deep inside these planets, thousands of kilometers down, the pressure becomes unimaginable. In 2017, and later refined in experiments in 2022 and 2024, scientists at the SLAC National Accelerator Laboratory recreated these conditions on Earth. They took plastic, specifically polystyrene, which is just hydrogen and carbon similar to methane, and blasted it with high-powered lasers to create shockwaves. For a split second, they created the pressure of a planetary core. The result was tiny nanodiamonds. The experiment proved that under high pressure and temperature, carbon atoms strip away from hydrogen and clump together. They form diamond crystals. Being heavier than the surrounding hydrogen-helium fluid, these diamonds sink. On a planet like the Lemon Planet, or deep inside a carbon-rich gas giant, this process is supercharged. In the upper atmosphere, methane and soot clouds swirl. Lightning strikes might turn methane into soot, essentially carbon powder. As the soot falls, pressure mounts in the middle atmosphere. The soot compresses into graphite flakes. As it sinks to the deep interior, the pressure exceeds 1 million atmospheres. The graphite structures collapse. They rearrange into a tetrahedral lattice. They become diamonds. These aren't just microscopic gems. These could be diamondbergs, potentially centimeters or even meters across, falling through the fluid layers toward the core. Near the core, temperatures might get so high that the diamonds melt, creating a sea of liquid carbon. It is a weather cycle of unimaginable luxury and violence. But how do we know all this? We can't travel 700 light-years to catch a falling diamond. We use a technique called transmission spectroscopy. When an exoplanet passes in front of its star, a tiny sliver of starlight passes through the planet's atmosphere on its way to Earth. The gases in the atmosphere act like stained glass. Methane blocks specific colors of infrared light. Carbon dioxide blocks others. Water blocks others. Before the James Webb Space Telescope, the Hubble Space Telescope could see water vapor well, but it was blind to many of the carbon signatures which glow in the mid-infrared. Webb carries two key instruments for this work. The near-infrared spectrograph breaks light down into a rainbow of infrared colors. It is incredibly sensitive to methane, carbon dioxide, and carbon monoxide. It was this instrument that sniffed out the carbon-heavy spectrum of the lemon planet. The second instrument is MIRI, the mid-infrared instrument. MIRI sees heat. It can detect cooler molecules and dust. It is crucial for finding the soot and polycyclic aromatic hydrocarbons, basically space smog, that indicate a high-carbon world. By analyzing the missing light in the spectrum, astronomers can reconstruct the chemical formula of the atmosphere. If they see a huge spike in methane and almost no water, they know the carbon-to-oxygen ratio is high. If they see the signature of acetylene, they suspect soot. Finally, we have to touch on the violent origins of these worlds, specifically the Black Widow systems. The discovery of PSR J2322-2650b introduces a terrifying new mechanism for creating carbon planets called stellar cannibalism. The lemon planet orbits a pulsar. This system is a Black Widow, named because the pulsar usually eats its companion star. However, in this case, the companion is a planet. One theory for its extreme carbon richness is that the planet is the stripped core of a white dwarf or a massive star that died. White dwarfs are the carbon and oxygen ash left over from a star like our Sun. If a pulsar stripped away the outer layers of hydrogen from a white dwarf companion, it might leave behind a diamond-rich core that effectively becomes a planet. Alternatively, the planet formed from the supernova debris itself, a zombie planet assembled from the carbon entrails of a dead star. This second-generation planet formation suggests that the universe recycles. It turns dead stars into diamond worlds. The discovery of diamond skies and carbon worlds forces us to rewrite our definitions of what a planet is. We are moving away from a binary view of rocky versus gas giant to a chemical spectrum. We have silicate worlds like Earth and Mars, made of sand and rust. We have carbon worlds like 55 Cancri E and the lemon planet, made of soot, tar, and diamond. And we have ocean worlds made of water and hydrogen. As we look deeper into the future of astronomy, the search is no longer just for Earth 2.0. We are finding worlds that are distinctly, beautifully, and terrifyingly different from our own. We have found the mines of Solomon floating in the void. We have found skies where the clouds are made of gems. And we have only just opened our eyes. The universe, it turns out, prefers its jewelry in the sky. Thanks for listening to this episode of G Fun Facts Online.